Hello everyone, welcome back to lesson number 3 for Calculus AB. This is where we're going to be finding limits analytically. And so in this particular video, we're going to talk about two strategies on how to find a limit at a given value. Up to this point, you found limits to infinity, positive and negative infinity, and then we also had a conversation about the definition of continuity. And that would be that the overall limit at a particular value as it's approaching is equal to f of a. So let me really quickly talk about, again, limit notation and a little bit what we're going to do with that. So here's my grid, and then I got myself a nice little function, pretty straightforward right here. And I want to approach some value of a, right? So I want the limit as x approaches some value of a. And so if we're looking at this particular problem, this example, we're approaching a, so we're on our function, and our function is approaching a from the left, and our function is approaching a from the right. We don't really care necessarily what's happening at a. We just care about what the function's doing, the behavior of the function at that actual particular value. So what we can now say with this picture is that as the limit, we take the limit as x approaches a, right, some x value of our function, it's going to be equal to, well, what's the behavior of our function around a? Well, it's going to be equal to the behavior of L. So what we kind of can say, if it's a continuous function, if it's a continuous function at that particular value, then we can just substitute in, right? Because AL is actually a solution to this function. Now I want to make sure that we're clear about that. That's not what the limit's telling us. F of a, this guy right here, that's what's saying that it's actually defined there. We're just looking at the behavior of it. But if it's a continuous function at that value, they're going to be the same. So that's why this is here. So what we can essentially do is the first method, and this is what you will always start with when you're trying to find a limit of a value, is you want to substitute. So the very first thing that we're going to say is that first thing you try for limits, and again this applies to limits to a value, not positive and negative infinity, but you want to do substitution. You want to try substitution first and see what's going on with that. So if you guys look at example number 1, I want to take the limit as x approaches 2 of this polynomial. Well, this polynomial is continuous everywhere. So this limit is just going to be equal to, if I plug in, it's just going to be equal to 2, oops, sorry, excuse me about that. It's going to be equal to 2 squared minus 4 times 2 plus 1, right? So this is going to be 4 minus 8 plus 1, and that's going to give me negative 3. So this limit as x approaches 2 of this function is going to be negative 3. So if I were to graph this function and I would look where x equals 2, this function would be approaching at y equals negative 3. Okay? So that's the idea from that very first example. If I look at example number 2, that you guys see right here, and I do the same thing, well then let's look at this one. So I'm going to go ahead and, again, it's continuous everywhere except for negative 1, right? And so I know it's going to be continuous, so all I have to do is plug in. All I can do is plug in, and I get 2 times 1 is 2, minus 6 is negative 4. I get 1 plus 1 is 2, which is 2, and so this answer to this limit is going to be negative 2. And then the final one, ladies and gentlemen, is now x approaches pi. So again, I know that this is going to be continuous. So I'm going to look at 2 cosine of pi minus pi. So everywhere I see an x, I'm going to plug in a pi. And then I'm going to start simplifying. So the cosine of pi is negative 1. So negative 1 times 2 is obviously negative 2 minus pi. I'm going to leave that guy by itself. And then the cosine of 2 pi is 1, and then 1 plus 2 is 3. And this is a legit answer. This is a legit answer that you guys will see. Sometimes you will see that they would pull out the negative, so for multiple choice, but I know you guys, calculus students, you know that you can tell the difference between the two of them, but that's really it. So if math could just be that simple, right? So substitution, that's the very first thing that you should always try when you're doing a limit, okay? Now, is it always going to work out nice like this? No, not very much. It's very common, very uncommon for this to actually work out as nice as it does, but you should always try it, okay? You should always try it. So what happens when we do something and we don't get nice numbers like this? So then if we look down here at the very bottom, it says if, when considering f of a, you get 0 over 0, the limit as x approaches a may or may not exist. So 0 over 0 is what we call an indeterminate form. Now let me say something really quickly about this. If we plugged in to our top and our bottom of our rational functions and we get something like 5 over 0, then that's okay. That's not an indeterminate form because one of our values is actually a constant. So this would be the limit, so straightforward, would just not exist because you can't divide anything by 0. On the other side of that, if I plug in something to a rational function and I get 0 over 5, well, then you know that this limit will actually just be equal to 0, right? Because again, 0 over 5 is actually equal to 0. So let's go ahead and plug in and look at example number 4 and number 5 and see what we can do with this, and then look at a strategy that we can take out of this problem. And so for this problem right here, it says let's plug in -2 to our function on the top. So we get -2 squared, which is 4, minus 2 times -2 minus 8. So this is going to be 4 plus 4 minus 8. So this top part right here is going to be equal to 0. If I plug in -2 in the bottom, I get -2 plus 2. Well, -2 plus 2 is also 0. So I know that I have what we call an indeterminate form here. So I'm going to tell you guys, you never ever want to set your limit equal to 0 over 0. That's something that College Board does not want us to say. So it's okay to have it on the side to say, okay, oh, there is an indeterminate, so we have to do something else to this problem. All right, it may or may not exist, but let's try what we want to do. So I tell my student we want to use some algebra. We want to use some algebra concepts. And the goal with this is we want to be able to manipulate this function or simplify this function, if you will, to where something cancels out. And then once something cancels out, then we want to plug in -2 again and see if we can get something other than 0 over 0. So in these two examples right here, so this is the first of our manipulation, and this is where we're going to factor. Okay, our fun friend of factoring. The other thing I got to stress with you guys right off the bat is that if you're going to factor or do any algebra manipulation, if you still have variables. Now examples 1, 2, and 3 at the top, you guys notice that I went ahead and just started plugging in, and everything that was left and all this work that you guys see in color, it's all numbers. So I didn't need to rewrite the limits on there. So just saying that if you are going to start manipulating your function, you got to keep this notation. You have to keep it, you have to keep it, you have to keep it. So if you just wrote the factor form here and not this, then you've now lost the integrity of the problem, and x could be anything, anything. Another little trick that I always tell students is if you get 0 over 0 and you think you can factor into the one that you want to do, then most likely 9.999 times out of 10, one of your factors is going to be what you see in the bottom, or the lone binomial. So if I go ahead and do this, I get 4 and I get this. So here's my function. And so just like before, I told you guys, we want to be able to simplify. And so luckily we are able to do such a thing. And then we're going to have the limit as x approaches -2. And then we're left with x minus 4. And now, ladies and gentlemen, it's not a rational function, or technically we could make it over 1, so we know we're not going to get 0 over 0 again. And by the way, another little thing is you always want to check, as soon as you simplify a little bit, you want to plug in, because if you don't get 0 over 0, then you're good. Then you're good. So I'm going to plug in -2. I get -2 minus 4 is -6. So this limit is -6. So what we would do if we were to graph this function is that there would be a hole here. Right, there'd be a hole at x equals -2. So visually, all right, so visually, what would this look like? So we're at x equals -2, and then we would down here at -6. There's a hole, and then the graph is doing something, like this or like this. It doesn't really matter which way it's going, but this is the idea of what it looks like. And so, ladies and gentlemen, this goes back again to what we talked about in the previous lesson. The limit still exists here. It's not continuous at x equals -2, but this is what we call removable discontinuity. So we talked about this in the previous video lesson. So it's removable discontinuity. And remember that removable discontinuity is the only type of limit, or type of discontinuity where the limit does exist. Because again, we're still approaching it from the left and to the right of -2 at some value. Again, we don't care what's happening at the point, but we do care that the behaviors are the same. So you don't need to know all that, but I just want to show you guys that that's what's going on in our graph, and then this is how we do it with our calculus. Okay? So let's look at example number 5. If I plug in 0, I'll plug in 0 to the top, I'm going to get 5. Well, I'm going to get 0 minus 0. If I plug in 0 at the bottom, I'm going to get 0 plus 0. So it's all going to be 0, 0, 0. So this is going to be a 0 over 0 problem. So we're going to factor, but this time we're going to undistribute. So the denominator, I'm going to go ahead and pull out an x. Right, I'm going to go ahead and pull out an x. And the numerator, I'm going to pull out a 5x. That looks like it's legit. And so I'm going to be left with x squared minus 1. Now guys, let me just say something really quickly about this example, is that when I start canceling out, I can cancel out these x's. Now yeah, some of you are like, okay, well you can factor this as x plus 1, x minus 1, and the x plus 1's cancel, but check this out. You don't need to do all that extra work, and we will to show that it works. But if I look at this problem and I get the limit as x approaches 5, or 0, sorry, of 5 times x squared minus 1 all over x plus 1, if I plug in 0 to the top, I'm going to get an actual constant. I'm not going to get 0. So I don't need to go and do any more extra work than I need to do here. So if I do this problem, I plug in 0, I'm going to get 0 minus 1 is negative 1. Negative 1 times 5 is negative 5. We'll plug in 0 to the bottom, I'm going to get 1. So I know this limit's negative 5. And we're going to go and do the extra step just to see, but to make sure that's negative 5. But yeah, so sometimes you want to simplify and then you want to stop. If you continue to simplify, then you may actually get a different answer. And that does happen. So once you simplify one thing, you want to make sure that you guys are good and kind of start plugging stuff in. But if we were to continue on with this question a little bit longer, then we would say, okay, well, let's take the limit as x approaches infinity of 5, and then be x plus 1, x minus 1 on top, and then x plus 1 in the bottom. And you guys will see it be kind of the same thing. The x plus 1's cancel out. And so then I'm left with 5. Let's change the color here so we can see it a little bit better. So 5. And then again, I'm going to plug in 0. 0 minus 1 is negative 1, and that also gives me negative 5. Okay, so 2 strategies for this, but I'm going to tell you that when you do cancel something out, it's always nice to plug in and see what you guys can do with that. All right, so hopefully that makes sense to everyone, and we're going to stop here for this one. So we've learned substitution and we've learned factoring. So what you guys can do is practice these other 2 questions here on the bottom. This one is clearly going to be substitution. This is going to be factoring, and hopefully you get the answers that are correct. So we're going to start with different types of limits with piecewise functions in the next video, and then some more algebraic problems that we can do. All right, so I'll see you guys in the next video.